Greetings and welcome to Probability Topics, Lesson 3.1, Terminology. Don't skip this important step. Go through each of your new terminology for this lesson. I want to quickly run through some terminology regarding experiments. Chance. Chance just means that the result is not predetermined. Just the chance of something happening. Outcome. Outcome is the result of an experiment. For example, if we were to toss a coin, the outcomes could be heads or tails. Sample space. The sample space is just the set of all possible outcomes. So we usually denote that as S, and sets are in brackets. Sometimes people call them curly brackets. So our sample space for a head toss is S equals the set of T for tails and H for heads. And it doesn't matter what order those two are in. Event. An event is any combination of outcomes. We can call event A getting at most one head within 3 flips. Probability is the likelihood or chance of something happening, of an event happening. Probability is a number between 0 and 1, including 0 and 1. If you think of probability, let's say probability of 0.25, you can change that into a percent, and that would be 25%. So probability is something that happens between 0% of the time and 100% of the time. If an event happens 0% of the time, then it can't happen. It happens 0% of the time. Versus something that happens 100% of the time is pretty much a for sure thing. It's always going to happen. So probability must be a number between 0 and 1, because when we translate that over to percentages, something can't happen more than 100% of the time. Yeah, I know you're putting 110% into this class, but that's different. That's effort versus the probability of something happening. Let's say we have an event, and that event is flipping a coin one time. Our outcomes for a coin can either be heads or it could be tails. So our sample space only consists of 2 things, an H for heads, a T for tails. Now, if this is a fair coin, meaning it's just as likely to land on a head than it is a tail, what is the probability of a head? Well, a head consists of 1 outcome for the 2 that it could be. So 1 out of 2. In other words, 0.50. What's the probability of tails? Again, that's 1 outcome out of the 2 possible outcomes, and therefore that's 0.50. When you take all probabilities and you add them together for a particular event, they must equal 1. So the probability of a tail plus the probability of a head is 0.05 plus 0.05, and that equals 1. All of our probabilities will add up to 1 for an event. Let's change our event. Instead of flipping a coin 1 time, let's flip that coin 2 times. Now the outcome for each coin flip is still heads or tails, but our actual sample space consists of 4 outcomes. The first flip could be a head, the second flip could be a head. The first flip could be a head, the second flip could be a tail. The first flip could be a tail, the second could be a head. The first flip could be a tail, the second flip could be a tail. What's the probability of getting 2 heads, 2 heads, HH, is only one of the possible 4 outcomes, so 1 divided by 4 is 0.25. What's the probability of a head first, then a tail? Again, that's only one possible outcome for the 4. So that's 1 divided by 4 is 0.25. What is the probability that we would get a tail first, then a head? That's only one possible outcome of the 4 that are probable, and therefore that is also 0.25. And the possibility that we get a tail and a tail on the second flip is also 0.25. If we add all these probabilities up, we do get 0.25 plus 0.25 plus 0.25 plus 0.25 equals 1. All of our probabilities add up to 1. Let's answer a couple of questions. First, what is the probability of flipping a head, then a tail? We've actually already looked at this, and that's the probability of an HT, head then tail, and that's 0.25. What's the probability of flipping one head in 2 flips? The probability could be H then T, because that's one head, or the probability of T then H, because we still have only one head. Therefore, 0.25 plus 0.25 is 0.50. Another object that helps us learn about probability is rolling dice. They're fairly standard. We'll go with the standard 6-sided dice. If you're familiar with it, each side has a different number, numbers 1 through 6. So if we roll a single cube, that would be rolling a die, D-I-E. And our sample space would be 1, 2, 3, 4, 5, 6. And each side has the same likelihood of being rolled. So the probability of rolling a 1 would be 1 out of 6, 1/6. What's the probability of rolling a 2? 1 out of 6, which would be 1/6. Each outcome has the same probability of occurring, 1/6. What is the probability of rolling a 3? Well, again, each side has the same likelihood of it happening, so that's one outcome out of the possible 6, so 1/6. What's the probability of rolling a number more than 4? Now, how many values on the dice are more than 4? Well, 5 is more than 4, 6 is more than 4. So we would have to add up the probability of 5 plus the probability of 6. 1/6 plus 1/6 is 2/6, or 1/3. What's the probability of rolling an odd number? Odd values are 1, 3, 5, 7, 9, 11. Well, on a dice, we have 1, 3, and 5. So we would add these probabilities up. The probability of rolling a 1 plus the probability of rolling a 3 plus the probability of rolling a 5. Therefore, 1/6 plus 1/6 plus 1/6 equals 3/6. In other words, 1/2. What if we roll 2 dice? What would be the sample set? What are all the possible outcomes? Well, on one die, you have the sample space of 1 through 6. On the other die, on the second die, you also have the sample space of 1 through 6. Now, here's a very easy way to figure out how many ways you can put those two things together. 6 times 6 is 36. There are 36 different outcomes when you roll 2 dice. A 1-1, a 1-2, 1-3, 1-4, 1-5, 1-6, 2-1, 2-2, 2-3, all the way up to 6-4, 6-5, 6-6. Now think about that sample space. What would be the probability of rolling the 2 dice with a total value of 11? What are the ways to get 11 on 2 dice? Well, one of them has to be a 6, one of them has to be a 5. So the first dice could be a 5, the second dice could be a 6. Or the first dice could be a 6 and the second die could be a 5. And therefore, there's only two possible ways of rolling an 11. So the probability of rolling 5 and 6 and the probability of rolling 6 and 5 would be 1/36 each. In other words, 2/36. What would be the probability of rolling the two dice with the total value of more than 3? So the dice total could be a 4, a 5, a 6, a 7, an 8, a 9, a 10, or a 12, right? Because two dice at the top value is 6, 6, and that could add up to 12. There's a couple of ways of looking at this problem. One is you can take every combination that is more than 3, like a 1, 3. Roll a 1 on the first die, 3 on the second die. A 1, 4, a 1, 5, and keep going and going and going until you find all the combinations that total more than 3. Or we can do something that's a little less work. What if we figured out what's the probability of rolling a 3 or less? That would give us a shorter way of getting to the answer. So if we figure out 3 or less, well, a 1, 1 gives us a value of 2. A 1, 2 gives us a value of 3. And a 2, 1 gives us a value of a 3. So that would be 3 out of the 36 possibilities. We know if we add up all of our probabilities, they do equal 1. They will always equal 1. So if we want to find the opposite, which is finding a total of more than 3, all we have to do is find the opposite, finding a total of 3 or less, and subtracting that from 1. So 1 minus P11 plus P12 plus P21. So it's 1 minus the sum of our 1 over 36 plus 1 over 36 plus 1 over 36. So 1 minus 3 over 36 is 33/36, and we can reduce that to 11/12. Sometimes utilizing what we know about all of our probabilities adding up to 1 is the shorter way to coming up with the answer. Otherwise, we would have had to do the probability of more than 3, which would have been 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, dot, 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 all the way to 6, 4, 6, 5, 6, 6. And we'd have to add all of those probabilities up. Versus, well, we just took the ones that are 3 or less and subtracted it from 1. Two types of events we'll concentrate on are or and. Or events mean that your outcome can come from set A or set B, or it's in both A and B. Let's let A be the set of 1, 2, 3, 4, 5, and let's let B be 3, 4, 5, 6, 7, 8. What would be the set of A or B? Well, as long as it's in one set or the other and we don't want to double count what they both share, then that means the set of A or B would be 1, 2, 3, 4, 5, 6, 7, 8. 4 and 5 are not listed twice. We don't have to list them twice. They're already counted when we list them once. Let's pull in another set, C. What would be A or C? So we're looking for things that are in set A or that are in set C. So the set of A or C would be 1, 2, 3, 4, 5. What would be the set of B or C? Well, that would be the set of 1, 2, 3, 4, 5, 6, 7, 8. We do not double count the 3 and 4. The second type of event that we look at is an AND. The outcome is an event of A and B if the outcome is in both A and B at the same time. So let's do A and B. Remember, A is 1, 2, 3, 4, 5, and B is 3, 4, 5, 6, 7. The only values that are in A and B at the same exact time are 3, 4, and 5. So the set A and B would be the set of 3, 4, 5. What would be A and C? Remember, A is 1, 2, 3, 4, 5, and C is 1, 2, 3, 4. The set of A and C would be 1, 2, 3, 4, since those are the values that they share in common. What would be B and C? We're only looking for those values that they share in common. So the set of B and C would be 3, 4. Let's talk about a few more event types. One is to be the complement. So let's say we have a sample space, and that sample space has the values of 1, 2, 3, 4, 5, 6. We'll call that sample space S. And we have 3 other sets. A is 1, 2, 3, 4. B is 2, 4, 6. And C is 1, 3. We want to find out what the complement is of each of these sets A, B, and C. For A, since A consists of 1, 2, 3, 4, A's complement, or A prime, that's that little mark there, what we call it, is going to be everything in the sample space outside of A. So A prime will be the set 5, 6. B is the set 2, 4, 6, and therefore its complement is everything outside of its set, so B prime will be 1, 3, 5. C is the set of 1, 3, and therefore C's complement, C prime, is 2, 4, 5, 6, everything outside of the set of C, but is still in the sample space. The last type of event I want to chat about is conditional. Conditional means, well, something's already happened. And when calculating the probability of an event given something else has happened, is this. I'm going to put together A and B for this instance. The probability of A occurring given B has already occurred is going to be the probability of A and B divided by the probability of B. Now, the probability of B can't be 0 because we don't want to be dividing by 0. We just want to be aware of that. So let's put this together. What is the set A and B? Well, that's the set 2, 4. And the probability of A and B is going to be 2 divided by 6 because our set AB has 2 elements and our sample space has 6 elements. So 2/6 is the probability of A and B. What's the probability of B? Well, B has 3 elements out of the 6 elements, so 3/6. Therefore, the probability of A given B is 2/6 divided by 3/6, which is 2/3. Now, that doesn't necessarily mean if we switch them around, the probability of B given A will get the same answer. So let's try it out. The probability of B given A is going to be the probability of A and B divided by the probability of A. Now we know the probability of A and B is 2/6 because their shared set is still 2, 4. We know the probability of A is 4/6. 2/6 over 4/6 is 2/4, in other words, 1/2. That is not the same thing as 2/3. So in this case, the probability of A given B does not equal the probability of B given A. Let's work through an example. The sample space S is the whole numbers starting at 1 and less than 20. S will equal the set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, because we are strictly less than 20. Let the event A equal the even numbers, and let the event B equal numbers greater than 13. The set A would look like 2, 4, 6, 8, 10, 12, 14, 16, 18. The set B would look like 14, 15, 16, 17, 18, 19. What is the probability of A? So count the elements in A and then divide by the count of elements of S. A has 9 elements. S has 19 elements. So the probability of A, 9 over 19. What's the probability of B? B has 6 elements. S has 19. So the probability of B is 6/19. What would the set of A and B look like? Remember, when we have an and, it's those elements in which they share. So the set A and B will look like 14, 16, 18. What would the set of A or B look like? So it could belong to A, it could belong to B, or it could belong to both. But we're not going to double count the things that belong to both. So the set A or B would look like 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18, 19. What's the probability of A and B? How many elements in A and B? How many elements of S? There are 3 elements of A and B, 19 in S, so the probability of A and B is 3/19. What's the probability of A or B? There are 12 elements in A or B, there are 19 in S, and therefore the probability of A or B is 12/19. What would be the complement of A? Now, the complement of A would be those elements that are in S, but not in A. So the A complement would be 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. What would be the probability of the complement of A, or A prime? How many elements are in A prime? There are 10 elements in A prime, and therefore the probability of A prime would be 10/19. You want to make sure that when you have the probability of A and the probability of A prime, you want to make sure those add up to 1, because you're taking all the elements in A and all the elements that are not in A, and therefore those probabilities better equal 1. So the probability of A is 9/19. The probability of A prime is 10/19. 9/19 plus 10/19 is 19/19. In other words, 1. Let's do one more check about something. Does the probability of A given B equal the probability of B given A? Let's just check these. Well, the probability of A given B will equal the probability of A and B divided by B. The probability of A and B is 3/19 divided by 6/19. That gives us 3/6 or 1/2. The probability of B given A is going to be the probability of A and B all over the probability of A. We know the probability of A and B is 3/19. The probability of A is 9/19, and that gives us 3/9, which is 1/3. 1/2 does not equal 1/3, so no. Probability of A given B does not equal the probability of B given A. You've reached the end of this lesson.